Hello class, in this video we want to address the question, can we tell if a function has an inverse or not? Or the more general question is, are all functions invertible? To do that, let's first recall the definition of a function. The definition of a function says that if y is equal to f of x, then for each value of x, there is one and only one value of y. So in other words, if I have a function that looks like this, okay, let's say it's a parabola. Okay, for each value of x, is there only one value of y? Well, yes, there is, because if you pick a value of x here, you only get one value of y. You pick a value x here, you only get one value of y. So this qualifies. Now, what about a function that looks like this? Well, let's say I pick a value of x here. I can see that there are two possibility value of y. There could be one, let's call that y1, y2. And that does not qualify. So this would not be considered a function. So in order for a function to have an inverse, that means the y mapping back to x has also to be unique. So let's take a look at this parabolic function here. If I have an x value, it's going to map to y by using f of x, right? Well, I have also another function of another value of x. Let's call this a, let's call that b. That happens to also map to the same value using f of x. Now, if I were to map it back using the inverse function, that means from the value of y, I should be able to map back to a single value in x, right? In other words, I should be able to backtrack and be able to get to a single value of x, hopefully. Well, unfortunately, in this case, it doesn't work because that same value in y can map back to either a or b. So this doesn't work. Now, what about the function to the right? For any value of x, I'm going to get a value of y if I'm mapping it using f of x. And then let's say I have another value of x. I'm going to map to a value of y, again using f of x. If this is a, this would be f of a. If this is b, this would be f of b. Now in the inverse function, I'm trying to map the y value back to x, correct? So in other words, f of b, whatever that value is, if I'm going the reverse direction by mapping it using the inverse function, it should map me back to b and nowhere else. And similarly, f of a is going to map me directly back to a only. Is that the case in this function? Yes, it is. So this is where we develop the notion that if a function has a one-to-one correspondence, meaning for every value of x, there is only one unique value of y that it maps to. There are no other values of x that would map to the same value in y. If the function has a one-to-one correspondence, then that means the inverse function will exist. Well, then let's ask ourselves a deeper question. If that's the case, does that mean that only one-to-one functions is invertible? Well, the answer is both yes and no. Yes, if you do not restrict the domain, then only one-to-one functions can have an inverse. On the other hand, if we are allowed to restrict the domain of a function, then sometimes we can make an otherwise non-invertible function to be invertible. So let's take a look. you recall a sine function is periodic, right? So in other words, every 2 pi values of x, the sign repeats itself. So for sure, there's going to be multiple values of x that is going to map to the same value of y. In fact, all these values of x, call it a, b, or c, would all map to, or d would all map to the same value in y. So for sure, this function is not invertible as it is, right? But can we make it invertible? Well, answer is yes, we can if we restrict its domain so that it's a one-to-one function within that domain interval. So let's say I'm going to restrict it to be right here. Okay, so this would be pi over 2, right? Sine of pi over 2 is equal to 1, and this would be my negative pi over 2. Okay, so if I redefine my sine function in such, so if f of x is equal to sine of x for if x were all real numbers, then this is not invertible. Okay. However, if I redefine sine of x to be x is in between pi over 2 and negative pi over 2, then yes, this is invertible. Okay, this is invertible. So the key message is sometimes you can make the function one-to-one by restricting its domain. As you can see clearly, the one that I highlighted in red here, that it is a one-to-one correspondence between x and y. Well, let's look at an example here. Let's say I have a function y equal to x plus 3 quantity squared. The function has a vertex at x equal to minus 3. I think we know that from algebra. And then I plotted out various points. So if I were to join them together, it's going to look something like this. Okay, not doing a very good job, but you get the idea. Now, clearly, because it's a parabola, and if I don't restrict the domain, this is not going to be one-to-one, right? There are multiple values of x that would map to the same value of y. In fact, you map minus 2, it's going to map to 1. If you take x equal to minus 4, it's also going to map to y equal to 1. So therefore, clearly, it's not one-to-one correspondence. So the function by itself is not invertible. But what if I restrict its domain to x less than negative 1? So negative 1 is right here. So in other words, if I were to restrict the domain to be x to be less than negative 1, I'm only looking at this portion of the curve. Does that make it invertible? No, because the problem of not being one-to-one still exists. So therefore, this function, as it is still not invertible. Okay? Now what if I restrict the domain differently? If I say the domain is now restricted to x greater than negative 1. So my negative 1 is right here. So x greater than negative 1 means I'm only interested in this portion of the parabola. Okay, and then it goes to infinity. Now is this one-to-one? Yes, it is. So this one is invertible. So the key message is just the fact that you're restricting the domain doesn't mean you automatically make the function invertible. You have to make sure that by restricting the domain, you have resulted in a one-to-one correspondence. All right, so just for completeness, let's see if we can find the inverse function given its domain restriction. All right, so you remember the procedure of how to find inverse. So I'm going to start with y equal to x plus 3 squared, and then I want to express some expression of y in terms of x, right? So I'm going to take the square root of both sides. So y would be x plus 3. Now I want to isolate x, so root y minus 3 would be equal to x. Okay, so in other words, my inverse function, if I express it using the variable y, means that is root y minus 3. And again, in my previous video I said we generally use x as the independent variable, so I'm just going to replace y with x, so root x minus 3. Okay, so that would be the inverse function. Now the last step is pretty crucial because we have restricted the domain of the original function to be x greater than -1. So in other words, we're only looking at this part of the curve. After we inverted it, root x minus 1, as I plotted out using this purple curve is root x minus 3, but that is not the inverse function. Because of the original domain restriction, we need to do the same thing with the inverse function. And since the original domain restriction is x greater than -1, in this case, after inverted it, we're only looking at this green portion. Again, this goes to infinity. Okay? So in other words, x in this case has to be greater than 4. Okay, for the inverse function to go hand in hand. All right, so in other words, let me rewrite the complete answer in green. The inverse function is root x minus 3 with x greater than 4. This would be the inverse function corresponding to the original function of f of x equal to x plus 3 square, where x is greater than -1. Okay, this would be the forward function in black and the inverse function in green.